welcome to today's webinar, CIBSE ASHRAE Group webinar. My name's Tim Dwyer. I'm a chair of the CIBSE ASHRAE Group and I'll be chairing today's webinar. With us, a world-renowned speaker who's going to talk about weather data.
Thank you, Tim. This is Joe Huang. I'm very happy to speak to this audience about weather data. And so first, before I start talking about the subject of weather data, I'd like to give some acknowledgments. These are 3 or 4 people that I've credit for giving me a lot of information about satellite-derived solar in various parts of the world, which is one of the most, to me, interesting developments in the recent, just very recent 5-10 years. And I want to give, because I'm going to be talking some of this data which we could all use in the building energy simulation field. So Tim asked me to do a self-intro, and that kind of puts me in a spot because, you know, I want to be truthful and don't want to sound like I'm boasting. I'm not a engineer, nor am I a meteorologist. I have a formal training in physics and a master's degree in architecture. But I'm also not really a practicing architect because just out of graduate school, I got hired at LBL. And I ended up staying at LBL, Lawrence Berkeley National Lab. I ended up staying there for 26 years. So that's the closest I could think of to having a career. So I've been a staff scientist at LBL for 26 years, specializing in building energy simulations and then using simulations to evaluate new technologies and to guide in developing building energy policy, which I got increasingly involved in the international field in the later part of my time at LBL. And so I mention that because that was actually how my interest in weather data began. It was purely because of need, because I noticed that when I go onto when I work on these international projects and I talk about the benefits of doing dynamic building energy simulations, the first question I always get is, well, do you have any weather data for my country? And in those days, in the early 80s, you know, it was pretty dicey. And I remember when I went to China in '85 on sabbatical, and I took along the DO2 program, a major part of my preparation was to find some weather data for China. And I ended up getting 5 years of 1 year of data for 5 cities. And that was, I thought at the time, quite an achievement. But now compared to what we could do now, you know, it's really just barely scratching the surface. So that was how I got started in weather data. And as the availability became greater, my ambitions also got higher. And so when I left LBL in 2007, I started a small company called White Box Technologies, and I continued working on weather data. Actually working on these weather data projects was one of the motivations for leaving LBL, because that wasn't part of my formal job specification at LBL. And so when I left LBL, it gave me the opportunity to work on several weather data projects. So I was a contractor for ASHRAE to develop the IWAC-2 weather files for 3,000 locations around the world. And I've also done weather sets for California Energy Commission, ISHRAE, that's the India equivalent of ASHRAE. And then in 2012, I launched basically a web store. I just launched this website to provide weather products and services over the web. And it may be unique in that I'm targeting specifically the building energy simulation community. And just as a final note, I'm a former chair of ASHRAE TC42 on climatic information and also a former chair of TC47 on energy calculations. Okay, so what are the weather data needs for building energy simulations? Well, it's pretty straightforward. We need detailed hourly observations of temperature, humidity, pressure, wind speed and direction, and solar radiation. Now, all of these variables are routinely recorded by weather stations, except for solar radiation. Um, and For building energy simulations, we need two types of solar radiation. We need the global horizontal, what they call the GHI, and then we need the direct normal or beam radiation, the DNI. And since these aren't measured in standard weather stations, they're very hard to find. And as rare as the stations that do measure GHI, I've found that getting measured DNI is even more rare and practically non-existent. So then what do we do about this? On all the weather files that you've seen, probably until the last couple of years, the solar radiation value are always derived from models. They're calculated. And it's only been the last few years that we now have satellite-derived solar radiation that we can now use. So a little bit about formats. I won't spend too much time on it. Just keep in mind that when you talk about formats of weather data, I see them in three categories. First is a raw data format. That's the data format, or that's the format the data comes from the weather station, or in the case of the first one, the ISD, it's the process, the format that they use to save it. Then there's METAR, which is almost like a standard that are now used to pass along weather data. So those are raw data formats. And I would think most of us, unless you really have an interest in weather data, don't even see these formats. Then there's the process formats. Those are formats that people have used when they've actually processed the weather data, filled in all the holes, and put in the solar and all this. These are formats that could be used in building energy simulations. And I just put the ones that I know in the United States. Both of these were developed by National Renewable Energy Laboratory, NREL, in Colorado, and those are the TMY2 and the TMY3 formats. The data in them is exactly the same. It's just that TMY2 is a fixed field format, so the columns all line up, and the TMY3 is a CSV format, comma separated variables, so you could import that into Excel. Then lastly, there are the simulation program specific formats. And those may be the ones that people are more familiar with. And these are specific to each program, each simulation program. The EPW for Energy Plus. That actually is exactly the same as the TMY2s or the TMY3 in their contents, but they're kind of put in a different order. And then the last two are related to the DO2 program. So I want to spend a little bit of time talking about what types of weather data are used in simulations. There's typical year and there's actual year. And actual year is pretty easy to explain. It's just the actual year. Typical year is an attempt to create like a representative year, sort of a snapshot that you could use if you don't want to run 15 years of weather data. Then there's observed data. All the stuff we're using until very recently, it's all observed data. It's from weather stations. And now we're beginning to also see synthetic data. By that I mean what they call reanalysis data or climate modeling data. I'll talk a little bit about that towards the end. And then I won't even touch upon the last one. The last one is using summary data, and that was something people used to do when weather data was really hard to find, so people use statistics and then they generate these hourly weather profiles that not done much anymore because there's no need to do that. There's enough actual weather data. So first I want to talk about the typical year. a typical year weather file is not a creation. You're not creating something new. It's basically an exercise in selection. And 95% of the work is not in producing the typical year, but in producing the historical weather data, the actual year data, 15 years or 30 years that you need, from which you then select your typical months. Now, when we first talked about typical year data in the early 80s, there were different methods that were proposed. Like one is TRY, test reference year, which is actually you pick one year that you think is the most representative. But those methods have all kind of dropped by the wayside, and now the consensus, at least in the United States, is in favor of the TMY method that was developed by NREL in the early 1980s. And the TMY method is actually the same as a test reference year method, except it's not trying to pick one year. It's trying to pick 12 months, each month of which is considered the most representative for the period of record. So I like that idea because to expect 1 year to where every month is representative is a little bit hard. So what you do with the TMY method is you find 12 months and then you just link them together. And the way you choose it is also, I think, very logical. They use or they came up with a term called the Finkelstein-Schaefer statistic. And what that is, it's a mouthful, but all it is you say, you plot the cumulative frequency distribution of a climate parameter, for example, the maximum temperature of the day, and you plot that from lowest to highest, and you do that for all your years that you have that you want to use, and then you plot or you calculate the long term. You add them all together, and then you get a frequency distribution for the long term. And then the Finkelstein-Schaefer statistic just says that that's the area enclosed between these two lines, between the actual year line and the long term. And then the month that you should pick is the one where that Finkelstein-Schaefer statistic is the smallest. This sounds pretty logical and straightforward, but then it gets complicated because you have to deal with 12 months, and then each month you have to evaluate it for 9 climate parameters, average temperature, maximum temperature, solar, wind speed, etc. And on this plot, what you see is this is actually New Delhi, January, and what you see is there's 20 years of data there, and the red line the bold red line is the average, the long-term average cumulative frequency distribution. And then all the little thin wiggly lines are the individual years. And then what you want is you want to pick the year where that line matches the long term the closest. And in this case, it would be the orange line, which is 2002. However, the month that we actually picked for January is 2001, which is that light blue line, or light blue colored thick line. And that's because we also have to consider other variables like solar and wind and humidity. And so you may be that what's going on is 2001 is not the best just for temperature, just for average temperature, but it's better than 2002 in the other things. So this is a very quick summary of how you develop a typical year file using the TMY method. The only thing that is sort of subjective, I mean, I like the method because it's very objective. It's just a bunch of numbers and you do the data crunching and you can pick the year. The only thing that's subjective is what they call the weighting, because you have these 9 parameters, then they're not weighted equally. And so there's been some brouhaha, what's the right weighting? And so I list here the weighting that's used by previous projects. The TMY, the original TMY, and the TMY 2 and 3, they weighted pretty heavily for solar. You'll notice that half of the weight is on the solar. And some people complain that, well, you're weighting the solar too much. But the effect of that on what you end up is really unclear to me, because when you weight something more, it doesn't mean you give it more emphasis, it just means that you give more emphasis on the average condition for that parameter. So I found out that the weighting really doesn't affect things very much. You see here at the bottom of this screen, there's a paper that a Chinese professor working with me wrote, where she looked at like 900 weightings and looked at 2 climates, I think one in China, one in the United States, and found that regardless of what weighting you use, you end up pretty much with the same data. So I just want to mention that that some of these concerns about the weighting is overblown. Okay, so this is a quick list of typical weather files, typical year weather data sets that we have in the United States mostly, or I should say with which I'm familiar. And starting first with the public or the free ones, there's the TMYs. I won't talk too much about the third one, what I call TMYX, because that's a satellite-derived one. I'll talk about that later. But the first 3 are done by NREL, and they cover the United States, increasingly better coverage, 239 locations, then increasing to 1,000, and now it's over 1 million grid points. Then there's the CWEC is a Canadian one. That's done by Environment Canada. CZ 2010 was one I did for California. And then those are all the public ones. Then the ones after that are what they call commercial, or it's done by non-government agencies. So that's the IWAC 2s, that's done by ASHRAE, the ISHRAE, and then the last 2 are ones that I've done. And I should also mention at the bottom that I know the Energy Plus weather website also have other public typical year sets from various sources. Okay, now I want to talk about actual year weather data sets. This integrated surface database is probably the single most important reason why I ended up working on weather data, because it's opened the door to all the weather reports from all the weather stations around the world. The story behind it is the United States has an agreement with the World Meteorological Organization to be the world's archive of what they call surface observations, weather station reports. And so they've been doing this since, I think, the 50s, and they finally decided that, well, we're sitting on this gobs of data. It's not doing anybody any good. It's not doing humanity any good. So they ended up processing that data to some degree, and they put it online. And so they call it the Integrated Surface Database. And first, you have to get a license to it, but then after a couple of years, it's now completely open. Anybody could access it. The web address is there. This really opened the door, because what this means is that all the weather stations that are reporting to the ISD, their reports are now available to the public from anywhere in the world. I've gone through this database extensively. It's always been updated daily. There's about 2,000 some stations, but most of them are inactive. But of the ones that are active, I've calculated that there are about between 8,000 and 9,000 stations that we have enough data that we could create detailed hourly weather files. So what does that look like? Well, this is for the United States, about 2,000, a little bit over 2,000 stations. And for Europe, similar coverage. Actually, I found that the coverage in some other parts of the world, like in South Korea and Japan, is actually even more dense than it is in the United States. And each of these dots, there's years of data there that you could access. The only caution I should say is that this is just an archive, and so if you got the file, it's going to look like the first one, the DSI 3505. You'd have to spend some time in parsing that and figuring out how to decipher it. And this is just what I do. I go from that to an intermediate file where I throw away the data that's superfluous to my needs. And then finally I process that to the last format, which I call FIN for finished. And this is where then it becomes usable. It has a solar, it tells what station it is, its coordinates, etc. As impressive as talking about the ISD may sound, I also want to mention that there's something else that may be even in some ways more impressive, which is now with the internet, we have these internet websites that are weather websites, and they're people, volunteers, schools, institutions, even companies, they put up a weather station and then they hook up with these sites and then they upload their data. And this is not an endorsement or advertising. I just mentioned Weather Underground because I've worked with their site the most. They also seem to be one of the earliest and the biggest. Well, they claim they have over 100,000 weather stations just in the United States alone. All that data is actually accessible through the web. So this is like an order of magnitude more than even the ISD. And show you an example how much coverage there is. I was recently asked to participate in a venture to do monitoring and verification of buildings in Knox County, which is where Oak Ridge is, Knoxville. And they wanted, of course, the weather data. And I said, okay, I'll take a look and see what's available. If you look for the ISD, there's actually no ISD station in Knox County, because that dot in the middle towards the bottom, that's the airport. The airport's in the neighboring county. And then the other two dots are stations at Oak Ridge. Those are the only official weather stations in that area. But then if you look at all these other dots, those are all the personal weather stations that Weather Underground has. And what are these weather stations? I don't want people to scoff at them too much. I mean, I was surprised that in where I live, Moraga, which is a small town of about 10,000 people, you had like 5 stations. So I went and actually checked them out. And these stations, one is at a college, local college, and the other is at the high school where my kids went to school. These are, the measurement technology for weather stations have improved a lot in the last couple of decades. It's now all digital, and the characteristics of these weather stations maybe 20 years ago would have been considered Class A stations. They're measuring all the parameters, they're uploading 5 minutes. So these, to me, this is pretty good data. Okay, I'll give you another example of how this data could be used. I had a project where somebody at Harvard was doing MMV, so they wanted weather for their building. I went onto Weather Underground and I checked around, and I found a station that was within half a mile of their building site with 15-minute data. And then just to be safe, I also downloaded the closest ISD station, which is Logan Airport. And what does it look like? Well, this is what it looks like. The different color lines are, the blue line is Logan Airport. The red is the station that I finally used. No big surprises. It's pretty much what you would expect. Logan Airport is a little bit colder at night, a little bit less humid at night. And then during the summer, it's also a little bit cooler in the peak. And the big difference is in the wind speed, because Logan Airport, being an airport, it's wide open. At the Weather Underground sites in town, the wind speed is basically half. So the client was very happy to get this data because it just meant that he actually had local weather data for his building. It's almost as if he had put up a weather station on his building. Okay, now I'll go on to sort of my favorite topic. It's the solar radiation. As anybody who's tried to work with weather data for building energy simulations or maybe any weather data, you always find that the big problem is the solar because nobody measures it. And now we have the satellite-derived solar radiation, which in some ways actually flips the situation, because with the satellite derived, we may be able to get continuous coverage on a grid scale for the whole world to whatever resolution you want. So from being the hardest to get, this may be the sort of the most complete comprehensive climate element that we will have. The pros is that from satellite, it's universal coverage, it's on a grid, and it's already available in the US. The first one that I list is from a commercial company, but they limited from 1998 to 2009. Anything newer you have to buy, and then it's quite expensive. But now, just last year, NREL came out with the update of the National Solar Radiation Database. Does the same thing as satellite-derived solar, but they intend to update that once a year. So now we could actually get it from North America from 1998 to 2015. I've compared some of that data to measured data, and I've concluded that it's better than the model data. And the only disadvantage I see, and this was written maybe 2 years ago, the disadvantage is that if it's outside the release domains, and you're trying to get it from commercial vendors, it's very expensive. I remember hearing a price of almost $1,000 for one grid cell for 1 year. Okay, I just want to step back a little bit. How have people calculate the solar before we had satellite-derived imagery? Well, we used these empirical or physical models. This is a model that I've developed with a colleague in Japan, and it's purely physical model. It's a purely empirical model. It correlates the solar radiation to cloud cover, temperature change, humidity, and wind speed. And then we tune it to available measure data. And this was done for the IWAC-2s. And the problem was there's very little measure data. So we had to split up the world by these broad climate classifications, and then we calculated coefficients for each climate classification and apply that to all the weather stations in that climate classification. There's no sort of empirical evidence that this all works, but that was all we could do. Now, going on to the actual the satellite-derived stuff, this is the website for the NSRDB. You get this map, and then you could zoom in on the map, and then you zoom into your location that you're interested, and then you could just download the data, and then the data comes via email. And then from my colleagues in Europe, I've also found out that there are equivalent sites in Europe. And this is one that's a Swedish site. I won't try to pronounce it. I don't know how you pronounce it, A with a circle over it. But one thing I want to point out to my friends in the UK is that you have a geographical advantage that Britain is actually completely covered. So you could actually go to this site and get hourly solar, or even I think 15-minute solar from 1999 on until now. And then here's another site that I heard about. This is a EU site. It's hosted in France, south of France, and they have a much wider coverage. It's a European weather satellite, covers all of Africa, all of Europe, and also a little bit of, I think, South America. So what's the situation look like now? I plotted the domains of these various databases, and it's quite impressive. I mean, we have the NSRDB for the Western Hemisphere. We have CAMS, which is that EU product, covers all of Africa and actually covers half of South America. We have that STRANG for Northern Europe. We also have India. It's covered by NREL on a US-India project. And then I put here in dotted lines, I've also gotten in touch with people in Australia who are working with the Japanese weather satellite, the Himawari. That gives you a domain that's shown here in the white dotted line. I'm not promising anything. I don't know how accessible is that data. I'm looking into it, but to me, that's like the missing link. If I could get that, also get access to that data, we basically have the whole world covered. And I'm already beginning to use it. This was a very recent project that I had, very amusing to me. I got called by somebody in the UK who wanted a weather file for London City. The funny thing was when I looked at the coordinates, it's actually the city airport. It's not London City, it's the London City Airport, but we didn't know that at the time. And so I processed that data, and I noticed that the solar is wrong because you look at the bottom, the middle plot on the bottom, sky cover, there's no sky cover. So the sky is always reported as clear. So that's clearly not right. And because of that, the solar is a lot higher than it was in previous years. So what I did was I went to, I think I went to CAMS, and I just downloaded the CAMS satellite-derived solar, and I just substituted that in there, and now the solar looks pretty reasonable. And you know, I'm thinking that in the future we may just throw away all the modeled solar and just use all the satellite-derived solar if it's available. Okay, so the last thing I want to cover is what's called synthetic or modeled weather data. This is not measured data, it's called reanalysis. That's what it's called in the United States. It's using climate forecasting models that's been around for decades, but now running it sort of in a retrospective mode, seeding it with observed data, and then you get sort of a complete map of all the climate conditions. And when I first heard about it, maybe 5-6 years ago, you know, it was have very glowing reports. You know, one person even said, you know, maybe all our weather problems will go away because now we could get weather for any place that we want because these forecasting models will just cover everything, sort of like the satellite, except it's all modeled. Well, I'd like to give some caution to that. I think it has great promise, but the results I've seen are still uneven. And I also wonder if it really benefits our needs because like in the US, the forecasting models are on the 35-kilometer grid, which sounds impressive, except if you look at where the weather stations are and where the buildings are being built, it's all in cities, and in the cities, the coverage is a lot better than every 35 kilometers. So I don't know how much we're going to gain from this, but I'm definitely going to monitor it. Also wonder if there's a catch-22 situation here. Catch-22 is a term that came from a World War II novel where it says that if you could prove that you're crazy, you don't have to fight. But if you know that you're crazy, you're not crazy, so you have to fight. And I see a similar thing here, possibly. Climate forecasting is most accurate if it has enough ground observations to see the model. But if you have that ground observation, you don't need to go to forecasting. Let's see, going a little bit backwards. Okay. This I got from NREL. They, for their NSRDB, they have the solar all covered on a grid. So they needed to put in also some temperature data. And so they used, so they've actually gone to reanalysis. And this is a plot they gave me that they looked at 3 reanalysis products. And they picked the one on the right because they thought it had the best match to the measured data. But when I look at this, and I get concerned because you look at Phoenix on the top right, I mean, that's a match, but it's a pretty rough match in my mind. And so since they actually have the reanalysis data linked into their solar data, I just downloaded some and I compared it to measured data that I have from the ISD, And these are just some samples. I mean, in Oakland, California, where you would think it would perform pretty well because we have lots of weather stations in the Bay Area, it's okay, I mean, at times, but at other times, it's questionable. And then in another place, this happens to be in India, I went to that because I didn't have very good measure data, but I did have one station nearby, and so I compare that to the mirror data, the reanalysis data. I basically concluded I wouldn't recommend the reanalysis data because it was off by so much. It was off by more than 10 degrees C during the summer. I keep going backwards. Okay, so that's all I want to say about the data. I mean, I find it a very exciting time right now, or as exciting as weather data could be, because all these new products are coming on board, and a lot of it is available publicly for free, and all it needs is for people to actually understand it and then put it all together. So I just want to end with this comment, things to watch out for when you're working with weather data. Or with the weather data of the type that I've mentioned, the real raw data. And this is just some things that came to my mind from my experience. What is a timestamp? Keep in mind, like the ISD, everything is uniform. It's all reported in universal time or Greenwich Mean Time. And even the pressure. This I didn't even know until I started dealing with it for about a year. The pressure is not the actual station pressure, it's all adjusted to sea level. So you have to watch out for these things. And then the third thing was something that I didn't discover until fairly late in my ASHRAE project. There are some weather stations around the world, a lot of them in Australia, that only report during the daytime hours. So what that means is you look at the number of observations, it looks okay. You look at everything, it looks okay. And then when you plot it, you get these really weird profiles because there's no data between 6 p.m. and 6 a.m. So these are things you have to watch out for. And then the last one is one that I've been talking about for years. There's a difference in the way solar radiation is reported on the weather files between North America and Europe and maybe the rest of the world. In the US, the simulation programs and the weather data, they always report the solar radiation over the past hour. So if it's the 6th hour, it's the solar radiation from hour 5 to hour 6. In Europe, and also in Japan and Australia, lots of places that I've talked to, the solar radiation is the average rate at that hour, at that time step. So there's a 30-minute difference. And you may think that's not very important, but it could lead to very weird effects. I mean, I had somebody in India say that, gee, why is it on your weather files you have more solar radiation on the east than the west? And it turned out it was because there was a 30-minute difference in the time zone. So these are things I just want to say. If you want to look into the data, these are some of things you may want to pay attention to. And then the other thing I want to say is if you're trying to evaluate the quality of the data, often we forget that 87, 60 hours is actually quite a lot of data. And I just want to show you the way now that I've developed to look at the data that I produce. I mean, I've been producing so many weather files that I can't, I don't have the time to open up each one and plot it and all this. So I've, with the help of a friend, I wrote an Excel spreadsheet that does all this automatically. And the first thing I do is this is very obvious. You just plot the time series. So it's dry bulb, dew point, pressure, total solar direct normal, sky cover, wind speed, wind direction, and rain. And this just gives you a sense, are there things that are really out of whack? But because there are so many hours, there are lots of things that looking at the data like this would miss. And so I've also developed this other way, using the same data and the same spreadsheet, but I find this very diagnostic. A very good diagnostic. What I do is I calculate the average condition on an hour-by-hour basis for all the days of a month. So what you have are like 12 days, one for each month, which is the average day for that month. And then I plot the time series for that average day. And what you see here is lots of things smooth out, but then there are some things that you could really pick out on. Oh, and I should mention on the right, I also find this very useful. On all this raw data, you have to know, what, or I misspoke, on all the process data, you need to know what are real data and what are interpolated data. It's like 3 hours missing, well, we will fill that in. Well, you need to know whether that is filled in data or real data. And so what I've done is I plot the number of actual observations or the number of missing observations by hour. And so here you see, this is, I think, someplace in the Caribbean. You see on the cloud cover, there's a lot of missing observations, but they're pretty uniform, so that's okay. But then if you have a location that closes down at night, you'll see a big band where there's never any observations at night, and then that would warn you on that data for those hours are all bogus. So I just found it very useful to look at the complete time series just as a first shot, and then the second thing is to look at the average day by month on an hourly basis. And so my conclusions, typical year weather files, they just provide a snapshot of the weather, and I encourage people to use historical weather files, particularly if you're trying to evaluate measured data. If you want to do MMV, or if you want to do an actual simulation of a building and compare it to what its actual usage is, you have to use actual historical data. I think one of the unintended consequences of the government coming out with typical year data is that a lot of people think typical year data, well, that's easy to get, and historical data, that's really hard. Well, it's actually the opposite, because to create a typical year file, you have to have 10 years or 20 years of historical stuff. But people don't, those are seen as intermediate files, and so there's a misconception that getting the historical year is very difficult. It's actually not. Then the availability of both raw and processed weather data has really expanded over the past decade. I hope I've convinced you of that. Satellite-derived solar radiation can transform what had been the most problematic to the most easily accessible climate parameter. Climate reanalysis, which is the forecasting models, they show promise for providing data for any place, any time, but I think it's still some time away. I think more attention needs to be paid to temporal variations in climate. I get annoyed when people just say, do you have a weather file for such and such place? And they don't seem to worry whether it's from 20 years ago or it's from right now. As long as it's that place, then they think they got the weather data that they need. And I think with increased attention to climate change, I think we should pay more attention and treat weather data like the newspaper. It goes out of date after a while. And then the last point was just what I said at the end. I find it very useful to use average days by month and the number of observations by hour of day to detect data quality issues. Thank you for your attention. I hope I'm not just talking to myself. If you have any questions, please forward them to Tim or to me. And here are my contact information. If you want to visit my weather website, there's the address.
Okay, thank you for that. And we have got some questions you'll be pleased to hear. So
Okay.
we've had an attentive audience, Joe, so thank you for that excellent presentation. Let's just go straight into the first question. And that was from this question is from James, and he says, well, why do you split it into year to months anyway? What isn't that arbitrary? Do you actually need to split this data into months?
Um, oh, you mean the typical year?
Yeah.
Yeah, it is arbitrary. I guess it's sort of the most obvious disaggregation down from the year. Yeah, it is arbitrary. I mean, you could do like 10-year periods. If you cut it too fine, you start running into, a lot of stochastic noise, Like I wouldn't want to do like a typical January 1 to January 7, You don't want to go to the week level because then um, it just gets too dependent on year-to-year variations.
Okay.
But yeah, it is arbitrary.
Okay. Thanks for that. A question from Tony here. He asks, how does bin weather data and the typical meteorological year weather data relate to each other?
Well, bin weather data, I mean, used to be the primary way people did analysis was with bin analysis. It's perfectly fine. The main disadvantage of bin analysis is that it loses the history, so you can't get the effects that it could be hot for the past day, and so that would have some thermal lag effects. You just don't pick those up. You don't pick up the historical effects. As far as actual, doing steady state calculations, it's basically the same thing.
Okay, thanks for that. Just a word of caution here from Mike, and he suggests that when using sources such as Weather Underground, but not explicitly that one, but such as that for wind speed, you have to be a little cautious. And he cites the anemometer on the high school in your hometown,
Okay.
as they're often located on building roofs, which can obviously have some localized effect on, if they're not situated appropriately, can have localized effect on that wind measurement. So that's something.
Yeah, that's a very true. I mean, that's very, very accurate observation. Although I found that the official weather stations are also guilty of that sometimes. I mean, the right way to do it is you need to measure 10 meters above the ground or something. But I don't know how many weather stations actually do that. And yes, wind is very site specific.
Okay, and of course there are world meteorological standards for that, aren't there? So people can actually refer to those, but of course you won't always know that Weather Underground or whatever the source is actually has conformed to those. So, yep, that's an issue, I guess.
Yeah.
Okay, the next question from Panos here. He asks about the availability of weather data and whether they're free and readily available. I think you actually mentioned that in your slide set. And the slide, just to remind people, the slides, I think, Joe, you hope to be able to let us have a PDF of these slides, and they will be available on the CIBSE ASHRAE website, together with a recording of this, so you can go and check those links out that Joe's used. So he's asking which ones are available. Well, you've given us an idea of what ones are available, I think. Are there any restriction on how the data can be used? Could I guess he's given cites an example here. Could an app be produced to plot average temperature and precipitation from a data sets?
Well, I'm not sure which data sets he's referring to. I mean, if it's the public typical year, you could do anything you want with it. If you're talking about the ISD data, maybe that's what you're referring to, the ISD data. The World Meteorological Organization did say that you could use it, but you're not allowed to sell it. But then that's referring to the raw data. You know, if you do anything with it, like post-process it, which I've done, I've checked that out with NCDC quite a bit. They said no, then that becomes another product and it's okay. I'm not sure what he means. I mean, you know, most of the sources that I've mentioned, the ISD and the Weather Underground, I don't think there are any restrictions against what you do with it. I mean, it's all public data as far as I know.
Okay, well, I think he'd have to look into that more closely if he was going to do a commercial product. I've got a question here from Pablo. He asks, can we just use the RET screen data? And of course, RET screen's the Canadian product that comes with some weather data files, I think. Can they be used in the same way as perhaps the Energy Plus data is used? You know, is that a source of reference?
I don't know that much about the RET screen data. I do know that that I've talked to people there, and they've listed white box technology as one of their sources, as one source for weather data. I do have to give a caution that I think there's too much sort of indiscriminate copying of free weather data, and you know, you have to take a look at it, like the Energy Plus weather website. Some of that data is really old, and the provenance is also not well understood. And just because it's free doesn't mean that you know, it's good. And so I don't have anything specific to say about the RET screen because I've never looked at it.
Okay, that's fine. And just I think that's absolutely true. Just because it's free does not mean that it's always good. And Panos has just come back to us, a guy who was asking about the app, and he was just confirms he's talking about using the freely available data. So that's good news. Next, we've got a query from Vikram, and he asks about Vikram asks about it's perhaps a little bit technical. This could be a bit lengthy to discuss here. How do you convert Weather Underground data to CSV? And I guess that could be found out from a bit of Googling around, could it, Joe?
Well, I mean, CSV just means it's comma separated variables. And if you get data from Weather Underground, it's actually CSV.
Oh, right.
So it is in the CSV, but that to me is the least of your problems. I mean, all this raw weather data, they're liable to have gaps. Their value, their units may be different. I mean, it will come in a CSV, but then you have to convert that to something that you need.
Okay, that's fair enough. I'm whizzing you through, jokes. We've got a lot of questions here. I hope you don't mind.
No.
Here's a really.
Hope the audience doesn't mind.
Here's a really good one. Well, they're all good, but here's one which is particularly interesting from Adalberto, and Adalberto asks, "How do you deal with microclimate in commercial projects?" Which is a tricky one, isn't it?
Yeah, well, it depends how micro you want to get. I mean, are you really talking about neighborhood, or are you talking about really at the building? I have several thoughts about that. One is, I believe, I mean, there are two ways to get microclimate data or very site-specific data. One is just use Weather Underground because they have so many stations. So you could get a station that is, you know, within half a kilometer of your site. That automatically should get you microclimate variations. The other way is one that I think the professionals are more intrigued by, which is to do modeling. And there are a bunch of microclimate site modeling programs, and they've been supported by various institutions for quite a number of years. And one that comes to mind is called WRF, that's supported by the U.S. government. There's also MM5. I personally think that, to me, it's easier and more reliable just to get actual measure data if you could find them, like from Weather Underground, because you can model it. And ASHRAE actually had a project to do that, to model or develop a tool to model a whole city for a year, and then you could get microclimate variations within the city. But the downside is you'd have to run a pretty fast computer for about a month. And if all you want is the microclimate for your site, why not just find where you have actual data? I mean, that's just my opinion.
Okay, thank you for that opinion. We've had a few questions. I'm trying to whiz through these questions and try and draw them together if I can. We've had a few questions including from Huang and James and others, just asking about. And I know, Joe, you had to leave this out of your presentation today because of a shortage of time. But future climate. Is there a few words you can give us? Perhaps in just a few words.
Yeah.
Okay. How's that affecting our climate data?
Well, I mean, future or climate change. I mean, the way that a number of people have dealt with that is what they call they stretch or they morph an existing file, and I've done that. It's not very hard to do because you could go to these sites, like in the UK, you have the Hadley Center, and you could actually download the projected change in climate into the future. So they'll give you the change in the mean and the range by month for temperature, and I think some other things. I don't know if they did humidity. And then you take those changes and then you just map them on an existing weather file. And that's not very hard to do. And I think that's what some of these programs that I heard about recently, like Climate Shift by Arup, that's what they do. And my only caution is that there's a lot of assumptions there. You're assuming that the thermodynamics of the atmosphere is basically the same. It's just a shift. And I worry that if there's more heat in the air, then it may become more unstable, so you have more extremes and more intense extremes. And doing this kind of shifting doesn't get that at all. So I have mixed feelings about the morphing. I know it's being done, and it's not hard to do. I don't know if it's capturing all the effects. The other thing that I'm regretful about is I think more people should also look at the trends of the actual weather and also use that as another data point to project out into the future. All this climate change modeling is fine, but it's still just a model. And we could look for other signals in the existing data, and I haven't seen anybody do that.
Okay, thanks. I was just distracted myself a second there. Sorry about that. Just to say that there is, if I was just trying to get a page up, but I can't multitask well enough here. If people Google CIBSE, CIBSE TM49, there's a free publication that's just been published that looks at the whole methodology of design summer years for London. This is, but the actual methodology equally appropriate across the world, and that may well help people in looking at the effect of future climate. So that's CIBSE, CIBSE TM49, and it's freely available as a download, so you can
Okay.
go and read that.
So it sounds like that is looking more at design conditions.
It is, yes.
Yeah, changing design conditions.
Yes, it's a design summer year. You're absolutely right.
See, my thinking was that the climate shifting and the morphing, that's probably okay for getting the change in energy consumption over the whole year. I'm more doubtful about the validity of that for the design conditions, for the reason that I mentioned earlier, that I've heard that with climate change, you could expect the extremes to get worse, more worse.
Okay, it's obviously a complex subject which we in a few seconds we're not really able to tackle properly today, but something for a future webinar, Joe, we could organise to discuss this. Well, I've still got a raft of questions coming in, but we've actually I see on my clock here in London we've run out of our time. Joe, it's been excellent. It's an area that that we all use all the time as designers and as academics, but to have it explained in the clarity you've done it today has been refreshing and incredibly useful. So thank you very much for your explanations, and also for the words of caution you gave at the end there in terms of the appropriate use of data. So thank you.
You're welcome.